Mojtaba, please go ahead. The floor is yours, and tell us about how analog gravity resolves theoretical physics problems, please.
Okay, thank you. Um, I'd like to talk about analog gravity and particularly about information paradox in theoretical physics and how analog gravity could resolve this problem. We go through to analog gravity, what is analog gravity, and how people see the analog gravity in laboratories, and then go through information paradox. And at the final, we get back to island prescription and analog gravity. Okay, what is analog gravity? If we've got a fluid, a rotational fluid, we've got this equation for a rotational fluid, the Navier equation, and continuity equation. If we change the variables, we can get to this equation and rewritten this equation in terms of scalar field theory in a background spacetime. So a fluid in a flat spacetime could play the role of scalar field theory in a curved background space. So this spacetime, this curved spacetime, could be a black hole. In this way, a fluid can mimic a black hole, but the difference is that in black holes we've got a speed of light, but here we've got a speed of sound. So these are some solutions in fluid. We call it dumb holes because wave sound cannot escape these regions. Okay. In laboratories, people produce some dumb holes in this setup. There is a wave generator, there is a barrier. When the waves go through the barrier, the speed exceed of sound wave, and then this region could be the dumb hole. So if you turn on a speaker here, the sound wave can go through the dumb hole, but they cannot escape. And this is a natural dumb hole, a drone. When we turn on a speaker here, the sound wave can escape this region. Okay. If we want to simulate an ADS Schwarzschild black hole, we just turn the metric of ADS Schwarzschild to this form by change of variables, and then compare the metric of ADS Schwarzschild to analog black holes or analog space-time, and then we can read off the fluid quantities. Rho is the density of the fluid, and V is the speed of fluid. So if we want to simulate ADS black hole, ADS Schwarzschild black hole by a fluid, we can just prepare these quantities in our laboratories, then the fluid mimic the ADS Schwarzschild black hole. Okay, let me go through this part and skip this part. Okay, information paradox. We know that if we've got a field theory in a curved background, this leads to Hawking radiation. Hawking radiation is thermal radiation. If the black hole started by the initial state of black hole would be a pure state, then at the final stage of evaporation, we know that the state of black hole is a thermal state. This is in contradiction with the unitarity of quantum mechanics. We can show this by entanglement entropy. Entanglement entropy is defined as the trace of density of matrix. We know the density. We know that entanglement entropy by unitary evolution is constant. It doesn't change. So when we start by a pure state and then goes to a thermal state, entanglement entropy wouldn't be constant. So this is the paradox. Okay. People believe that holography can solve this problem, the information paradox. But before that, let me draw your attention to the page curve and page works. A page showed that, I wouldn't go to any details, just go with the result. A page showed that if you've got a black hole and a medium, and the black hole evaporates, but page actually consider quantum systems, not a real black hole. So the entanglement entropy of the system would be follow this curve. We call it page curve, and this turning point is a page time. So if any quantum system follow unitary evolution, we expect the system, the entanglement entropy of the system follow this curve, page curve. Okay, people how consider entanglement entropy in holography. This is done by the celebrated formula of Ryo and Takayanagi. Sergio talked about entanglement entropy, so I skipped these parts. This formula got some problems because they cannot compute the quantum corrections. People try to alter this formula, and finally, people propose that if we've got this formula, which is called island formula, this island formula can, retrieve the page curve for evaporating black holes. But the point is that this island formula is really ad hoc solution to information paradox because people just add in some terms with no reasons. We'll show that analog gravity can explain why we should add these terms, but in a non-ad hoc manner. How people compute entanglement entropy via island prescription. If we got two-sided black holes, ADS black holes because we are working in holography, in ADS spacetime, the black holes reach equilibrium and they cannot evaporate out. So we should attach some thermal bus to the boundary, and then black hole evaporate, Hawking radiation goes through the thermal bus. And if we want to compute the entanglement entropy through island prescription, before the page time, we should compute the area of these patches. And after the page time, we should compute this area because this area is detached from the other area. We call it island. So if we want to compute this island prescription for a two-sided black hole, find that the entanglement entropy of the black hole follows the page time. So this is a resolution. But as I told you, this is an ad hoc resolution. How analog gravity provided region to island prescription. If we compute the entanglement entropy of an evaporating black hole, this is the term we get before the page time. This term is time dependent, and this is responsible for information loss because after the page time, this time blows up and then the entanglement entropy doesn't get back. So this term is responsible for information paradox. We work on this term in analog gravity, and we showed that this term could be translated to the information loss of the fluid over the wormhole's horizon. So if we simulate a black hole in a fluid as a wormhole, we see that this wormhole evaporates and people observe Hawking radiation in laboratories. And if we want to translate this term, this time-dependent term, we'll see that this term is analogous to momentum loss over the horizon of the wormhole. Okay. We see that these black holes are stationary, so if we apply on the horizon of these wormholes, we see that the momentum going into the wormholes would be equal to the momentum going out to the wormholes. But the island prescription doesn't consider the going out momentum, momentum going in. So if at this momentum, we'll see that we get to this. This is exactly what island prescription proposed. So, analog gravity showed that if we apply Newton's second law on a downward horizon, we can get to exactly the same result of island prescription. But here, this is not ad hoc solution because we apply Newton's second law, which is really trivial for our dynamics. Thank you for listening. And
Amazing. Thank you so much, Mojtaba. Actually
you.
finished super in time, according to this way earlier. So I think that there's a question from David. There's a question from Morgan. So David, you raised your hand first. So please go ahead.
Hi there, very nice talk. So I missed that little bit. Did you say that you can actually simulate ADS black holes in with correspondence or whatever?
Yeah, we can, we can build some fluid in laboratories that mimic exactly the dynamics of ADS Schwarzschild black holes.
Okay, and is that like arranged by some kind of reflective boundary conditions? Because one of the basic properties of ADS is that it's sort of confining, is that everything stays inside the ADS. It's like the box. Is that what you have, or do you have to impose some boundary conditions, or what do you do?
Actually, what we are obsessed is the equations of motion, only equations of motion. We're looking for a fluid that satisfies the equations of motion ADS black holes. That's it. This is different. I think you are considering holography, and in holography we consider all of things. But in analog gravity, we're just looking for equations of motion, identity of equations of motion.
Okay, thank you.
Morgan, if you want to go.
Okay, thank you. This is very interesting. I was curious about this. You had shown that there was an entropy associated with momentum. I was curious if you could just maybe tell me a little bit more about where that comes from, or how to maybe think about that, or just what is the nature of that? That was kind of an odd thing to see.
Actually, we see a real black hole. We see that the entanglement entropy is time dependent. And if we translate these black holes into a flow of quantities and stuff in analog, we see that horizon. Actually, we've got two different problems. The regional black holes and the analog black holes. These are different black holes. But we know that the equations of motion of both are the same. That's it.
That's interesting. Thank you.
Amazing. Are there any other questions from the audience? If not, thank you, Mojtaba, again, for your talk. It was truly very interesting.